Suraj, the broadcast has already
Hi
started.
everyone. Ah,
Yeah,
okay,
I think
okay,
we can
okay.
get.
Okay, super. Hi everyone. Thanks for tuning in. I am Suraj Dubey and today I'll be presenting on Kotlin Coroutines. I have been working with the Milezero capstone company for the past 4 to 5 years as a software engineer. And before discussing about Kotlin Coroutines, let's set up the context first. Uh, what with coroutines, what exactly is the problem that we're trying to solve here? Most of the code that we write nowadays are mostly related to IO bonds. What I mean by IO bond is most of the times the CPU is doing nothing, but it is just waiting for the operation from the either the database or either the file system or the network or the database to be finished. So application can be categorized into two forms. One is CPU bond, one is IO bond. There are other type of bonds, memory bonds, but that is beyond scope of our discussion. CPU bond, uh, CPU bond are the CPU bond are the processes which require intensive CPU utilization, and IO bonds are the processes where CPU just delegates the task to one of the controllers and just waits for the response to come back. So with with uh, with the evolution of microservices or mobile applications, even nowadays backend is talking to the backend, mobile front end is talking to the web backend. Within the microservices, the backend is just talking to another backend and just waiting for the response. And in those cases, it's we want the CPU to be not sit on idle state and put it under the maximum utilization. So this is the motivation uh, that we want to handle as much as IO based application as much as we can, and we do not want to waste too much of our CPU cycles also. So this and so how coroutines, how Kotlin tries to solve it in a neat and hygiene way is something that we're going to discuss today. Uh, and what we are going to discuss in short is what are the current approaches. This problem is not definitely new to us. So what exactly are the current approaches which we solve them, and how coroutines enables us to write asynchronous code in a very synchronous manner. We will go through some of the coroutine keywords, and everything is code in the end. There is no absolute magic happening anywhere. So we try to understand what is the code that is getting generated, some parts of continuation, passing styles, structured concurrency, about movement channels. We just go with brief in them. So let's try to understand what exactly are the current approaches that we have to solve the asynchronous programming. Asynchronous programming is where you just send where you just keep on waiting. You just send the request and wait for some data to come. The very first approach that we have is callback. What essentially happens is you send a request, and within the callback you get the response, whether the response has been received successfully or there has been some exception. And this has worked quite well. So, and this works quite well for certain use cases. But the moment you have a scenario where you want the response to of one API to be consumed by some other API, and the response from some second API to be consumed by third API, when you want to do some sort of chaining, it becomes very cumbersome. We all know that, and this is just one of the, and it's such a big problem that there is an entire Wikipedia article and a website dedicated to it, callback help. This is just doing three operations, and you see that the code becomes super messy to read. So, what exactly are the other approaches? And the other problem that callbacks have is, suppose if I want to fire up the same request multiple times, if I want to fire up the same request 10, 20 times, and so it becomes very difficult. It's not something that is impossible to do, but it's certainly very, very difficult. The next solution that we have for writing asynchronous code is futures. And most of us have been using some form of, if we are into Java world, most of us have been using some form of future library in one or the other way. Uh, so this is one of the example where we want to process certain request. Say it's a social networking site and someone has tried to add some friend and we want to process that. Uh, so you have a token that you have to get the details for that token, and then that token is going to return you one user. You do some processing of the user request, and then you try to do something else. This works fine. This works fine, at least better than callbacks. But the problem comes here is that uh, future implementation of future, it's not same everywhere. Right? You have to learn different combinators. You have to learn different keywords. And even if you are supposed to do some same operation multiple times, the flexibility that we have uh, in sequential kind of programming, say with for loops, conditions, and everything else, you don't get that knowledge here. But it does solve the problem in neat way. Uh, the other alternative to future is RX, reactive programming, which again causes the same problem that we have with the future, that you have to learn its own set of keywords. And most of the Okay, so that was about callbacks. What we've learned so far is that asynchronous programming we have been trying to solve using callbacks. That gives us the problem of callback help, uh, and futures, which works fine. But then handling exceptions could super messy here. And if we have to do same set of operations multiple times, uh, we do not get that. We'll have to learn different combinators. For example, here just for these two requests, we have to use then compose then accept. Uh, so that's a part. And one of the other problem is, suppose if we have three requests and all of the three data, say if you have to pass token and user to another API request, then you will have to use another combinator. You run another combinator, and it becomes very painful if you have to pass huge amount of data to the downstream. It's not that it's impossible to do. It's something that becomes getting trickier and trickier as we go on. So this is exactly where coroutines come into picture. It's not a very new concept. It has been there in some of the earlier programming languages as well. Coroutines lets you write the asynchronous code with asynchronous behavior in a very neat and synchronous way. And that's the context of the problem statement that we're going to solve. Now, for the most of what we're going to do is most of what I'm going to rather present is going to be mostly in the form of code. So let's get in there. So I'm just going to create a new file here. And the purpose is we are going to write a code that does a synchronous work. And then we are going to extend that to use asynchronous behavior. So network request example, this is just going to be a Kotlin file. And let me just really quickly get the I have worked on this, so I'll just quickly get this URL from here. We will have a private method that just gets the data for us. Return response string, and we are simply going to print off this data. Data equals get data, and just print this data. Super, super and nice. And we will just check, validate if it works. Uh, okay, so probably I'm trying to run it for the first time in this project, so it's going to take some time. Gradle is going to initialize the virtual machine, but the subsequent code should be faster. And yes, it does work. The surprising part is I'm printing the data twice. I shouldn't be doing that. It might confuse, so I would rather have it here. Okay, nice. Nice and easy so far. If we try and understand which thread is it running on, so we can print that thread information here and we will see that uh, it is indeed running on a main thread. No surprises there. The problem is that we want to keep main thread as free as possible, and we want to offload all this kind of tasks to the other thread uh, because we want to utilize concurrency multi-threading as much as possible. And the problem is in some of the frameworks, in some of the, for example, in Android, you won't be able to do anything on the main thread because main thread or the UI thread should only be ideally used for drawing on the UI. So let's see how we can convert this code into a synchronous behavior. Well, uh, for the purpose of this talk, we won't go and uh, for the purpose of this talk, we won't go and get into callback feature. But if you just want to get a quick look at it, I have written callback based implementation for my own purpose. And you will see that this is how it comes. We are using retrofit here, one of the networking libraries from Square. And you will see that we enqueue, we get the callback, and then we print the information here. And very easily, if we have to make the second network request, then we will get back to the problem of callback that we just discussed. Okay, so Kotlin, the whole idea behind coroutine is that that let's write asynchronous code that otherwise becomes very messy to write in a very nice and synchronous way. And we will just add few keywords to it. We will explain what those keywords are later on, but for now, I will just use this suspend keyword somehow, and then we get a compile time error in IntelliJ IDEA saying that it should only be called from coroutine or another suspend function. The moment we add suspend, we are telling telling to Kotlin that hey, this may involve some work which this may involve some suspending work, and the requirement from compile here is that uh, well, you go ahead and run the code. Well, you go ahead and run this suspending function, but make sure that you either call another suspending function or you run it from the coroutine. And what that means is now uh, main. If you notice, main is not a suspending function, but get data has been marked with the suspend keyword. So we will just go ahead and use a magic keyword that we will understand getting later on what exactly is it doing. Is global scope, or I would rather use uh, run marking. We can just use this run marking keyword and call get data in it. Nice. And if we run it, we will notice that we are still getting the same response. Nice and easy. But Uh, what exactly have we got after wrapping our source code inside run marking? Uh, so let's try and understand this part a little bit more. Uh, so we will just create another coroutine file, another Kotlin file, where the idea is just going to be uh, where we're going to just explore more of this Kotlin keywords, coroutine keywords. So this is one of the examples. We are just going to say launch coroutine as a file name, and this is going to be the file. We are just going to have a main method in here. What we're what we're trying to what we're going to do right now is we are just going to create a very simple coroutine. Uh, Private suspend modifier get data that is going to take one integer as an input and going to return one integer. We are going to use a method, a very dedicated method called delay. What it is going to do is it is not going to mark the thread, uh, and we are just going to. I'm just going to pass artificial delay of one second, 1,000 millisecond, and then we are just going to pass whatever the number that was passed into us, and then now we are going to call this get data with some parameters, say 10. We get this usual error here, error here that hey, please go ahead and use a coroutine, and we know what is the solution for that. For now, we will just go ahead and use this magic keyword moboscope dot merge and do the get data here. There is another magic keyword. We are just going. So what exactly is going to happen is, and let's try and understand what happens when we do moboscope dot merge here. The moment we have done moboscope dot merge, we are just saying that hey, we want to merge a coroutine just which we are just going to launch fire and forget kind of coroutine. It's not going to return any data to us. So what is going to happen is immediately line number 6 to line number 8, and I would rather go into there is presentation mode. I should have done that earlier. My apologies. Okay. So if we see here, line number 6 to line number 8 is executed, and the control immediately comes. Uh, the control immediately comes here to line number 9 and program simply exist. While what we want is we want to hold off until we see the response of this get data. So for that we are just going to use thread.sleep here. We are just going to put it for say 10 seconds, and whatever data we are going to get from here, we are just going to print it. Print and data. We will run this file and okay. It ran the other file. Sorry. So we'll see that we are getting 10 as a data here. We are getting the after a delay of a second, we are getting 10 as a data here. But what happens if we just remove this comment out this thread.sleep? Uh, we know that it's going to come here, and it will be asked to put itself on a suspending mode for a second. But then the program execution is going to come here, and then it's simply going to exit. So that's the reason we won't see this output. And just to see that output, what we are doing is we are commenting out, we are uncommenting out this thread.sleep. Well, so far so good. What exactly is the benefit we are getting here? Well, now we will try and create the same thread. So let's create a thread now. Get data with. I'll rather just put uh, thread example, and we are just going to use thread start equals to, and We are just going to print some random number for now. Print, say 40. That's it. And we are going to run this. So we'll just go ahead and comment out this for a moment. And we are just going to set thread example 40. So far, so good. But now let's try and run hundreds of threads. Let's see what happens. So to run 100 of threads, we have this sum of the for I in 1 200. We are going to merge hundreds of threads now. In fact, what we can do is we can just print I here. So far, so good. Let's try with few more. Let's try with 10,000 threads now. And if you see here, what we will do rather is we will also measure the time it's taking to run this program. So we have time equals. This is a very nice shorthand syntax. Measure time in English, and if you see the internals, it's exactly what you would expect. It's just going to get the current time, and it's going to run the code of execution, and it's going to minus, like it's just 10 minus start, like we using it, and we're just going to print, hey, how much time did you take to run this? Please, time taken to run thread example is time. Super nice. We see here, it's actually in milliseconds, should be in milliseconds, ms, yes. We see it takes about half a second, but if I just go add one more zero to here, so we will see that the time increases even more, and it will be roughly around, probably around 4 seconds for now. Yeah, we guessed it right. It's 4.7 seconds. Now, coroutines are essentially multi-bit threads. So what do we mean by that? So let's just go ahead and create hundred thousands of coroutines. So we will just have this coroutine example, and rather than this, what we are essentially going to do is we are just going to use the construct that we used above, that is global scope.merge print I. That's it. And now we are just going to do, we are going to remove this. We are going to call this coroutine example. Now let's see how much time it takes. Wow, I'll just run it again. Nice. The problem, though it is showing 167 seconds, we shouldn't be too surprised here. What has happened here is, if we, okay, what has happened here is that coroutines have been launched, but by the time their output has come out, they've printed something. The code of execution has reached to this stage, and that's why you see time taken to run before some of these outputs have even popped up, which is fine. So this is what it means by coroutines are very easier to, are very cheap, are very lightweight threads. You can instantiate millions of them, and you still won't notice huge performance difference. Whereas if I just do this a million times, if I just add one more zero here, my laptop would get stuck, even though it's probably the latest MacBook that we have here. So that's for the part of uh, what we are going to understand now is, let's try and understand what we have done here. So this is one of the source. So this is one of the code that we have. We will go with this easier example at first. Hmm. Okay, let me come back out of this presentation mode. Nice, nice. So let's take one of the examples here, and let's try to make this code as an asynchronous code. Probably the context is we don't want to block any thread, and we want to still execute thousands of these. So the very first thing that we noticed was we used something called as a suspend modifier here with respect to the function. Now, this does not have a proper anything to suspend inside, otherwise we would have seen that. But that's fine. We have seen in some other examples like here where the suspend modifier is actually saying that hey, you are actually using a method that requires suspension. So let's go ahead and do this. Let's go ahead and try to call this multiple times. Very easy to do. For I in 1 until 100, we are just going to call this get data so many times. And we are just going to measure the time, how much time it takes. While time equals and print time to run is, and let's see. So basically, we're just going making get request to this hundreds of time, and it's what we want to achieve here is now we want to make all of these requests. Okay, sorry, my apologies. I should have put it in measure time in this. Super. So we will see now what we want to achieve is we want to do the same thing here, but now we want to make parallel request, or at least we want to make concurrent request. We see that this is taken up to 16 seconds. We should have put MS here. So how should we go ahead about doing that? Well, now this is where the another construct comes here. The another keyword we are going to talk about. The other keyword that we're going to talk about is async and await. By using those async and await, we can make the request in a concurrent way. So by using those keywords async and await, what we're telling is, well, what we're going to get is a deferred result, and let's actually start using that, and we will understand more about it. So we can just use deferred here, or rather, yeah. Let's even go with a very simple example. So we'll go back to the presentation mode once again. Nice. We'll just remove off this code as of now, or we can just start writing from here. So let's try and understand what happens with async keyword real quick. So this is just another function that returns some data for us. Actually, let's just use this method itself. Now, what we want to do is we want to so global scope. We'll first put the keyword, do one example, and then understand what exactly is happening there. So if we just return n from here, and this is deferred of int. By using this word deferred of int, we can assume that this thing is doing some expensive calculation here, some expensive calculations. By using this deferred, what we are saying is, hey, it's exact. Think of it as like future variable where we say that, hey, uh, I'm giving you a future. That variable will be resolved sometime in the future, but not very immediate. And whenever you want, you can check the status of that. So let's go ahead and see how we can use this. So the way to use this is uh, going to be same global scope.merge, and say we want to call this expensive operation 10 times. So for I in 1 up to 10, what we do is data equals get data with say 10, and nice. So results equals, and what we're going to do is just call map on these. Okay. Now what we're going to do is we're just going to ask, hey, you know what? For each of these results, and we can just see if we remove this here because this does not make any sense. We are specifying scope here, so we should rather just do run walking here. And we should just ask it to return this data. Anyways, nevertheless, we should so if we check here, uh, probably I have been writing code without explaining, so my apologies. So let me just clear this subboard for a very quick, and I will just write it in this way for 1 in 100, and for each of the entries, what we are rather going to do is we are going to launch one async keyword. We are going to launch one asynchronous process, and we are simply going to return this I. That's it. And what we are going to do here is in the run smoking is we are going to check get all of these data. Let me call deferred list if that's appropriate. Yes. So what we're going to do in the deferred list is We are just going to ask, hey, let's just wait for your result. So what we have specified here is that we want to start a process asynchronously, and it's going to resume in the background. And only when we are going to call this await keyword, it's going to get the result for us. So if you read the documentation awaits for computation of this value without marking a thread and resumes when default complete computation is complete. So when this default computation is complete, so we can as well just put delay here of 1 second, and we will notice that even though we have hundreds of these, uh, we are not printing anything. Sorry, so this still at this mark only. But you will, yeah. So that's the whole point. So let's go to the next session. So this was the demonstration of async and await. Uh, uh, so this async is going to return your default instance that is going to tell you, hey, we will have the result sometime in the future. And await is also used for coordination among threads. So we will just modify this example a little bit, and for all these values, what we want is we want to add from numbers of we want to. So let's imagine that this 1 to 100 is the number is actually process 1 to process 100. They're returning something here, and what we want to is we want to compute the sum of all of those values. And now this becomes very easy with this construct. What we can do is we can just uh, say where, hey, you know what, the result is 0. So let's just say result plus equals it dot await, and then we can just print and result here. Result is result, and if we run this, we get all the results from process 1 to process 100, hypothetically assuming that each of those processes is taking up 1 second. Now we are saying this that just by using these constructs, now I can use if loop, I can use if for switch, just like how would I use otherwise normally of those constructs. So let's go back to the other example real quick where we were in the network request and we wanted to we were in the network request, and what we will do is we will try to introduce some delay here, artificial delay of 100, and we know this is going to return you default instance of some string. Nice. We know that because we are going to make it return one global scope dot async. This is one of the ways to return the data from here, or the and the other way is I can just ask it to. So this is one of the ways, but you will notice that if we keep on using this construct, a lot of what we uh, write in the asynchronous way becomes super easy in the synchronous way. So I have written one example for retrofit, and you will see that, yep. So this is the callback, and this is how the code becomes super easy to write. So this is just one of the suspend functions. This is a built-in support for coroutine by retrofit, and you just see that how naturally I've just made one API call here, but if I had to make another API call, that would become super painful. You will notice that how easy it becomes. It's literally we are writing a synchronous code, we do not have to worry about threading and everything else. We just have to specify how we want to do it. We don't have to learn different constructs. We just have to use this suspend. And if at all we have to use async or any or all those keywords anywhere else, we have to use them appropriately. So that's the advantage we get here. The other part that we wanted to understand was what exactly is happening when the code routine is being generated. So how basically how is it that we are able to create so much of threads, we are able to create so much of coroutines, and uh, we are not at all how is it possible that we are able to create so much of coroutines, but that same example is not at all true for with threads. So what happens is the silver bullet magic is this continuation interface that you see here. The context is the coroutine context, and the resume is just a result data class that has some success or fail interface with it. So uh, let's see what happens. Say this, I just so starting, it was mentioned that there is no silver bullet or there is no magic happening. So what exactly is happening here? So let's say this is one of the core routines. In fact, what we are going to do is we're just going to put it side by side so it makes more sense. Retrofit test, where did you go, boss? Okay. So this is one of the, in fact, let me just rename it real quick. This, I will call this as first process. I'll call this a second process. Refactor, rename. First process, I'll call this as refactor, renames. Second process. Okay. Even though this code looks sequential, behind the scene, there is callback getting generated. It's just that it's not explicit. We don't get to see it yet, but the compiler is generating the callback for us. So that's the next part that we're going here. The part that we're going here is what exactly is happening with coroutines that is helping us enable this, write this beautiful and sequential code. So the moment we have the suspend modify here, and what is happening is one additional parameter called continuation is being passed. And if I just open the generated code for it here, somewhere here, 1 minute, I have to get exit out of the presentation mode. Exit presentation mode, Kotlin bytecode, decompile. If I open it here, now if we try to do side-by-side comparison of these two things, it it will make more sense. So you will notice that there is a continuation object. This is our method network with coroutine that we're discussing here. There is an additional continuation parameter being passed. And uh, it's just an interface like it was showed on this previous slide. And what has happened is someone has just we have just put the implementation of it here. The compiler has generated the implementation of it here. And what happens next is it this is the source code. It has two breakpoints, or rather two functions, two suspending functions. It has two suspending functions. So what the compiler has done is it has identified those suspending functions because, well, we are using the suspend keywords next to it, so there's no magic there. And what it has done is it has created a state machine and passed on that state machine to each of these methods. So let's try and understand what happens here. So this is state machine that we're referring to. Forget about this line, but it has a implementation of resume, and What is going to happen is this state machine will be passed. Request.first process is going to have that state machine. It is going to be this instruction is going to happen, is going to get executed at, and at one point of time it will be completed, and when that will be completed, this resume method will be called. This when this request.first process gets finished, this resume method will be called, and when that resume method will be called, we are going to come back to this network with coroutine method again. But we also notice that on the first statement, uh, apart from the other data that coroutines needs, it is setting the label to the very next action that it needs to do. So initially that action is probably going to be zero, but we see that right before executing its first coroutine, first suspending function, it has set its label to one. So what has happened over here is this one is this same method is going to get called again, and when this process is finished, this same method is going to come to this line now, state machine dot label equals to, and then it's going to but basically label is always going to be the next action that you're going to take, which in this process is going to be the second process that it wants to finish, and then the third process, and that's how the compiler is going to generate the source code for you. Let's see if someone has any questions in here so far. Okay, nice. So that's a part, uh, and I will just quickly go and briefly cover about some of the other tools. Other things we discussed about suspend, launch, async, await keyword in a while. We also talked about code generation. Continuation passing style is the continuation instance that we saw. It was just passing the callback. Continuation passing style or CPS can also be referred as a generic term for callback. Uh, Structured concurrency, one of the nice things that we get when working with coroutines is one of the very nice things that we get is suppose that this suspending function, this second process fails somehow and first process has started its operation, and I will just go into play a presentation mode real quick. Okay. So review the line number 28 and 29. Let's say that the first process it had started executed and some second process that somehow failed. What is going to happen then is the second process has failed, but first process is still in middle of some of its operation. And let's say we have 10, 15 processes like these where the last process or the some of the last processes are failing. But the ideal behavior in that case would be just to cancel out all other operations. Uh, Otherwise, they might just sneak other resources. That's just a waste of bandwidth. That's just waste of our resources. So what this coroutine approach also helps us do is it helps us if once you specify the context, and that's why you see this global scope.launch everywhere. That's the context. So whatever coroutines, whatever suspending functions are there in that within that coroutine scope, as and when they get if one of them gets failed, all other its parents suspending functions will also get failed. That is going to make sure that resources are not leaked anywhere. So that's one of the thing. The other part is flow. So this coroutine based approach also allows you to pass in list of values rather than just a single value that we saw here. We're always passing. And channels helps you make sure that the data can be passed from the data can be passed from one coroutine to another coroutine without mutating the shared state, which is cause of which is the core issue of a lot of issues, which is the core problem for a lot of issues. We will have a separate session, probably deep diving on some of these, what what we wanted to understand from this session was just a very basic brief overview of some of the things, get a decent understanding of it. There's not there's not at all uh, like a full presentation. We have then we will have a session, probably a session where we will understand how to integrate some of these things with some of the existing frameworks, and for example Spring, and see how that is very nice with memory consumption. How that is very nicely with our overall system health. So that's about it. Thanks for your time. If you have any questions, I am monitoring in the chat. So feel free to post your questions. And that's it. Thank you.